In this video, we will continue our look at conformations of cyclohexane, focusing on mono-substituted cyclohexane rings. Our first example of a mono-substituted cyclohexane is methyl cyclohexane. Keep in mind the name is methyl cyclohexane. This carbon is automatically at position 1, so we don't have to specify that it's at position 1. Now, when we draw our flat structure, we can draw it without showing stereochemistry. So we have the methyl group and we also have a hydrogen connected here. It really doesn't matter whether we show it with stereochemistry or not, because for a mono-substituted cyclohexane, it ends up being the same thing if we draw our methyl group coming forward or if we draw our methyl group going back. But as we go from a flat structure to a ring structure, we do want to start with the stereochemistry shown explicitly. So if you are starting with cyclohexane, then you should pick one of these, and I'm going to use this one. So this carbon on the ring is automatically carbon 1 because that gives the substituent the lowest number possible. Now, as we're going from our flat structure to our ring, we can call any carbon carbon 1. I like to use the headrest as carbon 1. I find it easiest to work with, so I will almost always have the headrest as my C1, and so that's what you're going to see on my answer keys and things like that. So just be aware of that. So if this is carbon 1, this is our headrest, and we know that we have a group that is up, and we have a group that is out and just a little bit down. Now, because we are using this representation to start with, whatever we have in front of the paper, that is on the top face of the ring. So this is my CH3 group. And then whatever we have behind the paper, behind the screen, that is on the bottom face. So it doesn't matter if you start with this representation or this representation, but you need to be consistent between what you start with and what you draw next. Once you get more practice with drawing chairs and doing your interconversions, you don't necessarily have to fill in all of the hydrogens all the way around, but I definitely want you to include the hydrogen at any carbon that has a substituent. So don't just draw the CH3, draw the CH3 and the hydrogen. Now that we have this chair conformation, how do we do the interconverted chair? Well, once again, we want to think about taking our headrest and folding it down. We take our footrest and we fold it up. And so what we get is a chair facing in the other direction. Notice we did not pick up and move the chair. We're still at the same position on the beach in our beach chair, but our footrest has become our headrest and our headrest has become our footrest. So that means that this was carbon 1, this is still carbon 1. So at carbon 1, we have our two substituents and our hydrogen is still on the bottom face and our methyl group is still on the top face. Now, if you had started with your carbon 1 in a different place, maybe you called this carbon 1, well then here is your methyl group on the top face and here is your hydrogen on the bottom face. So your methyl group is axial and your hydrogen is equatorial. Then when you do your interconversion, this folds down, this folds up. So our other chair, keep in mind this is now carbon 1. So on carbon 1, the axial is going straight down and the equatorial is going back behind the ring, and that is our methyl group. So it doesn't matter where you start. Just because I start here doesn't mean you have to start there, but wherever you start, you have to continue, you have to be consistent with your starting point. So if you drew this as your original chair and then you drew this one as your interconverted chair, that's not acceptable. If you start here, then what you originally called carbon 1 it is still carbon 1. If you have other substituents, if you are numbering this one 1, 2, 3, 4, etc., so that you're going clockwise, then that's 1, 2, 3, 4. You have to keep going clockwise. So wherever you start, just be consistent. One other thing that I wanted to highlight, when we do our interconversion, we started out with our methyl group on the top face, and we ended with our methyl group on the top face. Good, because that's what we started with, right? We have our methyl on the top face, so on the ring, the methyl's on the top face. In the interconverted ring, the methyl is still on the top face. The hydrogen started out behind the ring, so on the chair, it starts out on the bottom face, and it's still on the bottom face. So the substituents, or the hydrogens, are going to remain on the same face before and after an interconversion, if you're doing the interconversion correctly. But a difference that we have is that in our first chair, our methyl group is axial and our hydrogen is equatorial. But in our interconverted chair, the methyl group is now equatorial and the hydrogen is axial. So groups on the top face remain on the top face, groups on the bottom face remain on the bottom face, but groups that are axial become equatorial, and groups that are equatorial become axial. So always double check that to make sure that you're doing the correct interconversion. Now, in an earlier video, when we were talking about cyclohexane itself, we had a chair conformation and the other chair conformation, but keep in mind that there are an infinite number of other conformations in between. But because the chair conformations are the most stable, those are the ones that we focus on. So now, as we're looking at mono-substituted and later di or tri-substituted cyclohexanes, we are again going to focus on the chair conformations because those will be the most stable, and so most molecules will exist in those conformations. But do keep in mind in the back of your head that there are a bunch of other conformations that exist, especially because one conformation is converting into another. Remember that we are talking about an equilibrium process, going from one chair conformation through an infinite number of other conformations to get to the other chair conformation. When we were looking at cyclohexane, because these are all hydrogens and these are all hydrogens connected to these carbons, then one chair conformation is the exact same energy as the other chair conformation. But when we have a substituent, this becomes different. So let's put in that methyl group. So we can have our methyl group here, and that means our hydrogen is out and a little bit down. And then don't forget, when we think about our chair interconversion, this one is our carbon 1. So here we have our hydrogen down and our methyl group is out and a little bit up. So our methyl is still on the top face, our hydrogen is still on the bottom face. The headrest, which had the substituents, became the footrest that has the substituents. What was axial is now equatorial. What was equatorial is now axial. So that's a good interconversion. But this is not the same as what we saw with cyclohexane, because with the presence of the methyl group, that means we're going to have a difference between these two conformations. Here we have our methyl group in an axial position, and over here our methyl group is in an equatorial position. So what does that mean in terms of energy? Well, let's try to figure out the type of strain that they have. So one possibility is torsional strain, but because they are chair conformations, we know that all of the bonds are staggered, and so no torsional strain. What about angle strain? Well, because it's in a chair conformation, all of those bond angles are really close to the 109.5 that is desired for an sp3 hybridized carbon. So that leaves van der Waals strain. And this is where we finally have a difference. So if we look at our first chair, we have our methyl group axial. What else do we have on the top face of the ring? We have an axial hydrogen here, and we have an axial hydrogen here. So here we have an axial hydrogen down, 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 and then we have other equatorial substituents. Now, instead of just writing this as CH3, if we were to picture this as a tetrahedral carbon, then you know that you have your hydrogens sticking out. And what you should notice is that this methyl group is actually crowding with these hydrogens. It's really helpful if you do build a model and put your methyl group in the axial position and take a look at the spacing between the methyl group and the other two axial hydrogens on the top face. And so what we have here is some van der Waals strain or steric hindrance. So because the hydrogens of the methyl group are too close to the other axial hydrogens, then we have some strain. That means this conformation is less stable than this conformation. Right here, our methyl group is in an equatorial position, so it is very far away from any other atoms on the ring. Now, this type of van der Waals strain or steric hindrance is called 1,3 diaxial strain. Because if we are, this doesn't have to do with numbering, but if we just for a moment call this position 1, 2, 3, 1, 2, 3. So it's not on adjacent carbons, but it is further removed, but the axial group at 1 and the axial group at 3 are too close to each other. The axial group at 1, and now we're going to call this one 3, these are too close to each other, so there is some strain. So the 1,3 diaxial strain is kind of, it's a specific type of van der Waals strain. In our other chair, where the methyl group is in the equatorial position, well, all we have are hydrogens in the axial positions. So these three hydrogens on the top face are not too close to each other. So there's no diaxial strain there. All right, and then we have these hydrogens are the axial hydrogens on the bottom face, but because all three of them are hydrogens, then there's no 1,3 diaxial strain. So both conformations have no torsional strain, no angle strain. This one does have van der Waals strain, or more specifically 1,3 diaxial strain, which makes this less stable or higher energy. So this conformation then is more stable, lower energy, and this conformation is less stable, higher energy. This is an equilibrium process, and in this case, the equilibrium is going to lie toward the lower energy species. And so the equilibrium is going to lie toward the right. So we can draw it like this to emphasize that the equilibrium lies to the right. So if you could take a snapshot of a sample of methyl cyclohexane and you could see exactly what conformation every single molecule was in, you would notice that you have lots and lots and lots of molecules in this conformation. You have fewer molecules in this conformation, and then you have even fewer molecules in a bazillion different conformations in between. Now, what if we look at different substituents? So we're still looking at mono-substituted cyclohexanes, but let's compare what we have with a methyl substituent compared to an isopropyl, compared to a T-butyl substituent. Well, let's just fill in. Let's put our methyl group here and our hydrogen here. In our second one, this is our isopropyl group, and here is our hydrogen. And in our third one, this is our T-butyl group, and this is our hydrogen. In each case, we're going to do our ring interconversion. So we're converting one chair to the other chair. And now our hydrogen is here, and our methyl group is here. Our hydrogen is here, and our isopropyl group is here. our hydrogen is here, and our T-butyl group is here. Now, let's think about what we saw on the previous slide. We have 1,3 diaxial strain. So we have an axial hydrogen here on the top face and an axial hydrogen here on the top face. And that is present in all of these. Now our methyl group is going to be bumping into these hydrogens. Again, build a model. It's really helpful to see it that way. Because of the 1,3 diaxial strain, then that makes the first conformation less stable, and so the equilibrium lies to the right. Now, when we are looking at an isopropyl group, so the isopropyl group is much bigger and bulkier than the methyl group, so here our diaxial strain is going to be even worse, which means there's going to be a bigger energy difference. Right here, our isopropyl group, we've got no problems because this is in an equatorial position. Here, the isopropyl group is in an axial position and it's bumping into these axial hydrogen. So this has more strain than what we had here. And so there's going to be a bigger energy difference between this conformation and this conformation. And so for this molecule, the equilibrium is going to lie further to the right. And then in our third example with our T-butyl group, axial versus equatorial. So an axial T-butyl group, remember I drew this as a little t, but this is a carbon with a methyl group and a methyl group and another methyl group. So this is huge. So the amount of van der Waals strain, the steric hindrance that's causing these atoms to bump into each other, it's huge. So this has a lot of van der Waals strain, which makes the axial T-butyl group very, very, very unstable. And so this equilibrium lies so far to the right, I can't even fit it on the screen. So with different substituents, we're still going to have a preference for the big substituents being equatorial. But the amount of preference is going to vary depending on the size of the substituent. Now, table 4.1 from the McMurray textbook, this shows steric strain in mono-substituted cyclohexanes. And this gives a value for the 1,3 diaxial strain for different substituents. So we're talking about a substituent Y, and we want to think about how much more unstable is it if the Y is in an axial position, and this is a hydrogen, or if the Y is in an equatorial position. And so the diaxial strain can be given in kilojoules per mole or kcals per mole. And let's just take a look at a couple of examples. So let's stick with kilojoules. And we have a methyl group is 7.1. We have an isopropyl group is 9. And then a T-butyl group is 20. So a lot more strain because of the bigger, bulkier groups. Now this graph is in your book. It refers to a Gen Chem concept about different isomers, or it uses the term conformational isomers, which I do not want us to use. So we are not talking about the more stable isomer, we are talking about the more stable conformation, and then the less stable conformation. When we have a methyl group, here we have a difference of 7.1 kilojoules per mole, and this would be the difference in energy between having a methyl group equatorial versus axial. So what we're looking at, this is the energy difference between the different conformations, and this reflects the percent of that conformation that would exist in a sample. So at 7 kilojoules per mole difference, then we're going to have about 5% of our molecules with the Y in the axial position, and then we're going to have about 95% of our molecules with the Y in the equatorial position. If we have a really small difference, so if we're looking at bromine, for example, if we have an axial versus an equatorial bromine, then that energy difference is around 1.6, so we're around here, and so that means we're going to have about 30% of the less stable conformation and about 70% of the more stable conformation. As the energy difference gets bigger, then the difference in the percents becomes bigger. If we look at an isopropyl group, so the isopropyl group was here with a difference of 9. So now we are here, if I can kind of get a straight line. So now we're looking, this is going to be less than 5%, and then this is more than 95%. And then if we're thinking about a T-butyl group, well, this graph doesn't even go out that far, right? But looking at what this tells us, when we have even up to a 15 kilojoules per mole energy difference, we're going to have almost all of the molecules in the more stable conformation and very, very few molecules in the less stable conformation. So when it comes to a T-butyl group in particular, we say that the ring is locked into the conformation with the T-butyl group equatorial, because it is so difficult for the T-butyl group to go into the axial position that it essentially doesn't happen. So I wanted you to be aware of this. This can be quantified, all right? And there are calculations that you could do to quantify it. But for the most part, I want us to think about relative amounts. So more of a qualitative rather than a quantitative approach. You know, in general, I want you to be able to tell me that you're going to have more molecules in the conformation with a methyl equatorial than with a methyl axial, but you're going to have almost all molecules in the conformation with a T-butyl group equatorial and almost no molecules in the conformation with a T-butyl group axial. So qualitative, relative, this is what we are looking for. So this takes us to the end of the monosubstituted cyclohexanes. In our next video, we're going to look at what happens when we have 2 or more substituents on a cyclohexane ring.